Hi folks, welcome back. I hope you're all doing well. Today I want to take a look at a paper which looks at how one might drastically improve the virtual memory model that we currently have that works with fixed-sized pages as the unit of protection to a model that not only allows byte granularity protection but also adds in a capability model. The name CHERI in the title stands for Capability Hardware Enhanced RISC Instructions. What the authors are doing in this paper is proposing an extension to the instruction set architecture of a RISC machine to add a capability-based model of memory protection, but also one that operates at a much finer granularity. This paper is from 2014 and it adds this to the MIPS architecture, which was the predominant RISC architecture at the time. But one could really look at the CHERI set of instructions as an instruction set add-on that could work with any RISC architecture. In fact, if you check out some of their later work, you'll see how they've ported the same idea to ARM as well as RISC-V. Let's start by looking at what the requirements are for a good and also practical memory protection system. The first one is that you should be able to use it in unprivileged code. So this is obvious. It should not just be the operating system that makes use of it, but also user space. We want fine granularity so that you can actually protect structures that make sense in your program. You want unforgeability in the sense that once you have set the range of protection and also the type of protection that you want on memory, unprivileged calls should not be able to change that. And this protection should be enforced by the hardware. That's a fairly daunting set of requirements, but when you're implementing this in hardware, you want it to be as simple as possible so that chip manufacturers can indeed practically put them on their chips. And so what the authors are proposing in this paper is a memory capability model. A capability, simply put, is an unforgeable pointer that grants access to a range in the address space. And then the protection is enforced by having all memory accesses go through these capabilities. So to get concrete, in this paper, the authors have chosen to implement these ideas as an extension to the MIPS instruction set. But as I mentioned before, you can port the same ideas to other common RISC architectures as well. They implement this as a coprocessor. Think of it as analogous to a floating point coprocessor. And this holds its own register file and the logic around it. In terms of implementation, the authors are adding two main new abstractions. The first one is a set of memory capability registers, and the second is a set of instructions that are used to load and store these registers to and from main memory and change their contents. These new capability registers are 256 bits wide, and they consist of a base and a length. So those are the basic things you need to specify a range, a linear range of memory. And they also contain some space to hold permission bits. These permission bits are things that indicate whether one is allowed to load or store data or to execute as instructions the data stored in that range of memory and so on. Now note that we really want these capabilities to be unforgeable, but we don't want to do that purely in the kernel. You don't want to have to make a system call, which is quite expensive, every time you want to change a capability. And what that boils down to is that when these capabilities are stored in memory, you want to restrict how general user space code is able to change them. And the way the authors are proposing to do that is by essentially tagging these capabilities when they are in main memory. They're essentially using a tagged memory model. And these capabilities are marked with an extra tag bit that is associated with each 256-bit location. Anytime you write to such memory through a channel that doesn't go through the capability coprocessor, this bit is cleared, and then you know that this is not a valid capability anymore. And so that leaves you with only one valid way to manipulate these capabilities, and that's through user mode instructions, these new instructions that are added to the ISA. This new instruction set also enforces the property that whenever we change fields in a capability, we only reduce privileges and never increase them. And this makes them unforgeable essentially. If you try to relate this to the process model, a process would start off with a capability for its entire virtual space, and then it would be able to make finer grained capabilities for other purposes within its virtual space. So how might one actually use this? The most practical example, and also the one with probably the largest safety impact, is protecting pointers in C. So imagine a C compiler and runtime framework that when you mallocked a new pointer, it used one of these capabilities as that pointer, and it contained the full range of that pointer, the range that you just mallocked, as well as permissions, whether you were able to change this range of memory or whether you could treat this range of memory as executable instructions. And then all those properties would get enforced by the hardware. This would completely do away with an entire class of buffer overrun and stack smashing attacks. In fact, the authors have implemented this by changing the LLVM compiler stack to implement C pointers as memory capabilities. Of course, the stack itself is also just another range of memory, so you can use capabilities to protect the stack and ensure that stack smashing attacks cannot work anymore. If you're wondering how stack smashing attacks work, I have a very old video on this channel that explains that with a very simple example, and I'll link to that in the description. The only downside to this approach is that you'd have to recompile your application code with this new compiler stack so that pointers get treated as capabilities. There's also the pesky matter of dealing with the C standard, because the C standard and lots of C implementations will actually let you do all sorts of undefined pointer behavior that these CHERI capabilities will disallow. The authors have implemented this in an FPGA, a MIPS FPGA with added logic for their coprocessor. And the performance overheads for various benchmarks range from close to nothing to the 15 to 20% range, as you can see in this graph. But perhaps a non-FPGA implementation can get that even lower. I want to quickly relate this to another paper we looked at in this channel a few weeks ago called the carrot cake system. And that was a system that tried to do all of this memory protection completely in software. So that took a very, very different line of attack on this problem, which is that how can we do all this memory protection without any hardware at all, purely in software? And so that's another very different approach to the same problem. So that was a quick look at CHERI, which is a way to add a fine-grained memory capability model on top of a RISC architecture. I hope you enjoyed that, and I will see you next time. Thank you very much.